just the basics. So today we're talking about Bayes' theorem. And Bayes' theorem is you're going to learn how to apply Bayes' theorem and recognize when it applies. So a little bit of history behind Bayes' theorem is that Bayes' theorem was named after a guy, a reverend, Thomas Bayes, who was an English statistician, philosopher, and a minister. Okay, most of the work on the theorem and its interpretations, though, was actually done by a French mathematician, Pierre-Simon Laplace. Bayes' theorem is what lies in the heart, like the field of statistics, Bayesian statistics to be exact. And what it actually is it's the original conditional formula for probability. So conditional probability, the original was Bayes' theorem, okay? So once, folks started working with Bayes' theorem, they were able to condense it into what we now use for conditional probability, okay? It's what we now use for conditional probability. So with that being said, I'm going to show you Bayes' theorem next, okay? So these are the two different interpretations of Bayes' theorem. What you see here in the blue is like an abbreviated version of Bayes' theorem. So as you can see, it uses the same conditional probability line, but its probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. What you see that's not in like the blue shaded, that's actually the formula that's in your reference booklet, okay? And so essentially, like the denominator can really be like multiple events that are happening, okay? But it gives us a way to update probabilities when we're given new and additional pieces of information, all right? But it's a way to find probabilities when we're given additional pieces of information. So Bayes' theorem, like I said, is similar to conditional probability, but you use Bayes' theorem if you were given one condition, you were asked to find another. That's like one of the biggest differences between conditional probability and Bayes' theorem. However, a lot of the problems that I've run across, from being online to textbooks to even like the IB question bank, a lot of them are, you could get away with using conditional probability to solve them. But I want to go over an example where we're actually going to use Bayes' theorem to solve it, so you can actually see it. You can actually see it in action. Okay. So it says ball A contains 4 red balls and 3 green balls. Bag B contains 4 red balls and 1 green ball. A ball is randomly chosen from both bags. Find the probability that they are different colors. Okay. Now this is not Bayes' theorem. It's not. This is basic probability. Okay. As you can see, this is an A, B, C, D problem. So Bayes' theorem is going to come towards the end. Okay. So just working this out, a ball is randomly chosen from both bags. Find the probability that they are different colors. Okay. Well, this can happen if we draw from bag A, right? And then it's a red ball, and then bag B is a green ball, or bag A is a green ball, and bag B is a red ball, right? So, okay, let's see how I can write. Well, for the sake of the video, right? I want basically a red ball, given that it's coming from bag A, which means a green ball coming from bag B. Or I want a green ball coming from bag A, and then a red ball coming from bag B. Essentially, that's what we're finding, okay? But no need to do any serious conditional probability with that. We can pretty much just look and figure that out. There are 4 red balls out of the 7 from bag A, and then that means it'll have to be green from bag B. So that's 1 ball out of 5. If I'm drawing a green ball from bag A, that's 3 out of 7. And then a red ball from bag B, that's 4 out of 5, okay? That's what we did at the very beginning of probability, all right? This one is a non-calculator type of problem. So that's gonna be 4 over 35 plus 12 over 35, which is 16 over 35, okay? Not beige yet. Let's get to incorporate some other probability problems in there. Now it says a biased coin is flipped. If heads is shown, a ball is randomly selected from bag A. If tails is shown, then the ball is randomly selected from bag B. We have to complete the tree diagram. And we already know that the branches of a tree diagram have to add up to equal 1. So the probability of it being tails is going to be what?
1/3.
1/3, okay? Then if we go down the tails branch, what's the probability of it being green?
1/5.
1/5, okay? Let's go the heads branch. If I go the heads branch, what's the probability of red? The top. 4 out of 7. And then that means green would have to be 3 out of 7.
3 out of 7.
All right. Now, see, it says a biased coin is flipped and a ball is randomly selected. Find the probability that the ball is red. Okay, so the coin is flipped, the ball is, and a ball is randomly selected. Find the probability the ball is red. Now, remember, red can happen if it's heads in red or tails in red, right? So that's going to be, I'm going to put it up here. So red being heads or red being tails. So that is 2/3 times 4/7 plus 1/3 times 4/5, because that's getting head and then going red, or tails and then going red. So then that becomes 8 over 21 plus 4 over 15. We have to add those together. Common denominator, non-calculator, common denominator. What is the common denominator between 21 and 15? So our common denominator is 105, so that means we'll have to multiply 21 by what to get 105?
5.
5. And what by 15 to get 105?
7.
Okay. So then that's going to be 40 plus 28. So then that's going to be 68 out of 105. That does not reduce, I don't think. Yeah, that doesn't reduce. Now for part D, it says, given that a red ball selected, find the probability the biased coin showed head. This is an example where we can use Bayes' theorem, okay? This is an example where we can use Bayes' theorem. Real quick, I'm just gonna go back, get the formula, okay? We'll copy it over. This is an example where we can use Bayes' theorem, okay? We have a particular condition, and we can use this here, all right? So we want that the biased coin shows head, given that it's a red ball selected. So we would set this up as head, given that it's red. So then that means we want the probability of it being red, head, times the probability of head. All I'm doing is taking the Bayes theorem and plugging it in based off of our particular problem. They want the probability of it being red. And now I can use my tree diagram and Bayes theorem to do this, okay? Now again, I'm showing this example as an example for Bayes theorem. Yes, we could definitely do this a different way, but I'm trying to show you how Bayes theorem can be used here, okay? So, we want the probability of red given that it was a head on the coin, okay? Well, the way we can use our tree diagram to determine this part of the equation, we look at the tree diagram and we said, okay, it has to be red given that it was a head. So here's the head. We want the probability red given that it was a head. So that 4/7 is what is representative of what's boxed in yellow. Then we want to multiply this by the probability that we even get a head at all. Okay, so we want to multiply by the probability of getting a head. As we can see from the tree diagram, the probability of the coin landing on head is 2/3. So we multiply those together. Then in the denominator, we want the probability of it being a red ball, and we found that out back in part C. So our answer to part C is our denominator in part D. And now we can perform the algebra to find our answer to part D. So when we multiply it, that's going to be 8/21 divided by 68/105. Then we'll want to keep, change, flip. Since this is not calculus, try to reduce. We already know that 21 goes into 105 5 times. And we know that what number goes into 8 and 68?
4.
4. So that's going to be 2. 68 divided by 4 is 17.
Yes.
So then we'll multiply straight across to get 10/17. That's how we can use Bayes' theorem in a problem like this.